Hi everybody, and welcome to Unit 5 Notes. In Unit 5, we're going to talk about chemical reactions and being able to write chemical equations for those reactions. Before we get started with the reactions themselves, we need to talk about something that are known as diatomic molecules. There are 7 elements that are they're very reactive. They really do not want to ever be alone. All right. So when they are by themselves, they actually pair up with themselves to form a molecule. And we call these the diatomic molecules. And they are hydrogen, and you know, we write them H2, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. All right, you must memorize these. They're going to come up a lot in this unit and in future units. Sometimes a little saying that helps some people is, here no one fails chemistry but I. It's not very uplifting, but it does work. Also, using the periodic table, hydrogen you just kind of have to remember. All right. Otherwise, the other 6 actually make the number 7. All right. So we have hydrogen over here, then nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Those are your diatomic molecules. And as I mentioned before, we're going to be using those all of the time. Okay, so let's get started with our chemical equations. Chemical equations are our way of representing chemical changes, all right, or chemical reactions. All chemical reactions have what we call our reactants, and those are the substances that you are starting with. And then you will always have your products, and those are the substances that you end up with. All right, reactants will always be written on the left, then you will have an arrow, and then your products will be written on the right. All right, there are 5 types of chemical reactions that you're going to be responsible for. So let's go over those types. Okay. For each of them, I'm going to give you a little explanation. Then this here, where you see the A's and the B's, that's just kind of a generic equation to show you generally what it looks like. All right, so let's go through and see what we're talking about. All right, a synthesis reaction is when there is a combination of 2 or more substances and a compound results. All right, it's going to generally look like this. A plus B is yielding AB. You know, all right, because you're going to start with 2 or more substances all right, and you will end with 1 product. That's what tells you are dealing with a synthesis reaction. Okay, so let's do an example. All right, we are going to write the equation for the synthesis of water, from its elements. That's one way of saying it. Okay. All right. So synthesis of water from its elements. Well, I'm synthesizing water. I am making water, producing water. So water goes as my product. Well, what elements make up water? Hydrogen and oxygen. You have to remember hydrogen and oxygen are both diatomic. So that is the way that we write that. You may notice that right now I do not have the same number of elements on each side. We're going to go back and take care of that after we go over our 5 equations. All right, so let's look at our next type. And our next type of reaction is known as decomposition. This is the opposite of synthesis. Okay, it is when a compound is broken down into simpler substances. So for here, you're going to start with 1 compound. Okay, and you're going to end with 2 or more substances. Remember, substances can be an individual element or an entire compound. We're going to keep our examples pretty straightforward for decomposition. So here's an example. We're going to write the equation for the decomposition of sodium chloride into its elements. Okay, so the decomposition of sodium chloride into its elements. So sodium chloride, I still have to make sure that I write my compounds correctly. Sodium is +1, chloride's -1. Great. It's going to break up, decompose into its elements. So that's sodium and chlorine. We do have to remember chlorine is one of our diatomics. So that's going to break up into Cl2. Again, we'll worry about the fact that there's not the same number of Cls in just a moment. Okay. All right, great. Let's go on to our third type of reaction. And in our third type of reaction, we have what is known as a single replacement reaction. This is also known sometimes as displacement. It really just depends on the textbook or the worksheet that you're working on. You know that you're dealing with a single replacement because you will have a single element and then an ionic compound. Okay, so it is the reaction between an ionic compound and a single element. In single replacement, there's always a rule. All right, a metal is going to replace a metal, or if your single element is a non-metal, it's going to replace the non-metal. So let's look at some examples. Okay, let's start with sodium plus magnesium chloride. Okay, so I know this is a single replacement because I have a single element, sodium, and I have an ionic compound, magnesium chloride. All right, so my sodium is going to replace, that's why it's called replacement, or displace, same idea, the metal in this compound. I know it's going to displace the metal because sodium itself is a metal. Remember, as we look at our periodic tables, the metals are to the left of the stair step. Sodium is a metal, magnesium is a metal. So the sodium is going to kick the magnesium out. All right, and when that happens, sodium is going to go with chloride. Note that I only put one chloride here. There's two chlorides here because magnesium is +2. Well, sodium is only +1, so sodium chloride is NaCl. And then magnesium gets kicked out and is left over there. The same idea can happen if your lone element is a nonmetal. So let's go Br2, bromine, plus sodium oxide. Okay. All right. So first off, why is sodium oxide Na2O? Remember, oxygen's -2, sodium's +1, so I needed 2 of those. Writing formulas is never going to go away, so please refresh yourself on writing formulas if you need to. So I'm going to look at this and I'm going to say bromine is a nonmetal. Okay, again, bromine is one of my halogens. It's to the right of that stair step. It's a nonmetal. So it's going to replace the nonmetal in the compound. The nonmetal here is oxygen. So that's going to give me sodium, bromide, +1 -1, so that's the compound. And then oxygen is now going to be all by itself. Now remember, oxygen is diatomic. All right, and again, we'll come back and talk about the fact that we don't have the same number of things. Okay, our fourth type of reaction is what is known as a double replacement, also known as a double displacement reaction. All right, again, could also be called double displacement. So if you hear us referring to it as displacement, it means the exact same thing. And in this case, you're going to know that it's a double displacement because you're going to be dealing with 2 ionic compounds. And what happens is they switch partners. The metal from the first is going to go with the non-metal from the second. All right. They're going to switch partners and give you 2 new ionic compounds. So let's take a look at some examples. Okay. So I have sodium chloride plus silver nitrate. All right, here we go. I know it is double displacement because it's my only type of reaction that I'm going to have two ionic compounds. I'm going to switch partners. So it doesn't matter which one you go with first. I'm just going to say, I'm going to deal with my sodium first. So sodium is a metal. It's going to go with the non-metal from the second compound. Because remember, two metals will never go together. Two non-metals don't go together in ionic compounds. And we're going to be forming two new ionic compounds. Sodium is going to go with nitrate, giving me NaNO3. Sodium's +1, nitrate's -1, so that works out fine. My next compound is going to be my metal from here and my non-metal from here. Metals are always written first. Silver is +1, chloride's -1. This one works out great. All right, let's take a look at another example. Okay, so now let's go on ahead and we're going to do potassium carbonate plus magnesium iodide. Take a second here and pause and see if you can predict what the products are going to be. Okay, here we go. So my potassium, here is a metal. It's going to go with my non-metal, and that's going to give me Ki. Now, why just Ki? Potassium's +1, iodine's -1. That is the proper formula for it. Magnesium is going to go with my carbonate. Again, metal, negative ion. Magnesium is +2, carbonate is -2. There we go. All right, great. Okay. And our fifth type of reaction, and don't worry, you're going to get a chance to do a lot of practice with these. Our fifth type of reaction is a combustion reaction, and this is one you guys should be very familiar with from biology. Combustion reactions are where we take what is known as a hydrocarbon, all right, and that means it's going to be a certain number of C's, a certain number of H's. All right, we're going to react that with oxygen, and our products are always going to be carbon dioxide and water. Okay, always, always, always. So a combustion reaction is when a hydrocarbon reacts with oxygen and produces carbon dioxide and water. There's no figuring this out. All right, these are all covalent compounds. This is just what happens. Combustion is commonly known as burning something. All right, you also should remember it, as I mentioned, from biology, because cellular respiration, where we take glucose and it reacts with oxygen to give us carbon dioxide, water, and of course, energy. That is typically the major purpose of a combustion reaction. All right, and that's because it is an exothermic reaction, which means it gives off energy. So let's just see what one of these is going to look like. All right, so I'm going to take CH4, which is known as methane. You don't need to know that yet. And if I were to just say, write the reaction for the combustion of methane, all right, you know I'm giving you methane. This will always be given to you. And these three components are always, so there's no thinking about it. This is just what always happens. So it's going to be CH4 plus O2 is going to give me CO2 and water. Always, always, always. All right, great. Okay, let's do, sorry. Okay. We're going to stop. No, all right. We're also going to take a look at, let's do as an example, C2H6. Okay. This is actually known as ethane. And this, again, always is going to give, you're going to react it with oxygen, and it's always going to give us carbon dioxide and water. All right, great. Now, you may have noticed, and I mentioned it as we went through, okay, that we did not necessarily have the same number of atoms on each side of our equation. And we have to fix that because according to the law of conservation of mass, this is a big one in chemistry, mass cannot be created or destroyed in a chemical reaction. And that's what we're interested in right now, chemical reactions. Therefore, you must start and end with the same number of atoms. We do this by what is called balancing the equation. All right, we've already done a couple of these parts. We're going to write the formula for the reactant. We're going to predict and write the formulas for the products. We've already done that for our examples. We're then going to use coefficients to balance the equation. A coefficient, let's say I have a water molecule here. A coefficient is a number I would put in front. So that means I have 2 water molecules. Okay. Notice I'm not changing what water is. I'm just telling you how many of them I need. All right. Coefficients just give you multiples of the number of the substance that you need. Never, ever, never change the formula to balance the equation. We write the formulas first and then we leave them alone. All right, so let's go back and you're just gonna flip back in your notes and we are gonna take a look and go through and balance all of these equations. All right, so I don't want to make that messy. There we go. All right, so let's start with our first one, our synthesis. Okay, so I balance by looking to the left and looking to the right. So let's take a look. Hydrogen, I have 2 hydrogens here on the left. I have 2 on the right. Great, that's fine. Oxygens, I have 2 on the left and I have only 1 on the right. Now remember, never write the 2 there. That would change water into hydrogen peroxide, something very, very different than water. But I can make it so I have more waters. So I have 2 oxygens on the left. I only have 1 over here in water. So I'm going to say now I have 2 waters. Well, this 2 means now I have 2 oxygens, but it also means I have 4 hydrogens. That's okay. I have 2 hydrogens over here. I'm going to go ahead and put the 2 there, and that works out great. This is now a balanced equation for the synthesis of water. All right, let's take a look at our decomposition. Sodiums look good. Chlorine, I have 1 on the left. I have 2 on the right. So I'm going to put a 2 in front of the sodium chloride. And now I have to put a 2 in front of the sodium. Again, I'm using coefficients. I'm not changing what those substances are. Really, really important. Let's go to our single displacement. All right, so looking here, sodium, that looks fine, 1 and 1. Magnesium, 1 and 1, okay. Chlorine, I have 2 chlorines and 1 chlorine, so that means I'm gonna have to put a 2 there. My chlorines are now good, but now I've messed up my sodiums, so now I'm gonna put a 2 there. I'm good to go. All right, let's go to our second example. I have bromine on the left, okay, I have 2 of them, I only have 1 on the right. Can't change what this formula is, but I can say I want 2 of them. All right. Now I have 2 sodiums here. I have 2 sodiums here, looking good. I have 1 oxygen here, but I have 2 here. So that's going to be an issue. So I'm going to go on ahead. I have to balance those oxygens. So I'm going to put a 2 there. All right, well, that's fine. And now my oxygens are good, but if you notice now, my sodiums, I have 4 and I have 2. That's okay. That's why I use an eraser. So now I'm going to put a 4 here. All right. So my sodiums now look good, right? My sodiums look good. And I now need to check my other elements. So my bromine, my bromine's not okay because I have 2 on the left and I have 4 over here. So I'm going to put a 2 there. So now I have 2 bromines. 2 times 2, 4 bromines, 4 bromines, 4 sodiums, 4 sodiums, 2 oxygens, 2 oxygens. Now you are good to go. And sometimes it does take a little finagling and work to do these. All right, let's go on to our double replacement. Okay. A little advice when it comes to balancing double replacement reactions. Treat polyatomic ions as a whole thing. So rather than looking at this as a nitrogen and 3 oxygens, I look at this as a nitrate, as the entire nitrate, because the nitrates will pull over from side to side. It's just going to help you with time. All right, well, in this one, what's nice is if you notice everything was plus or minus 1, so it's actually kind of balances itself, but we should always check. So I have a sodium, sodium, good. Chloride, chloride, silver, silver, a single nitrate on the left, a single nitrate on the right, that one's already balanced. Okay, so now I'm going to take a look at my second example. Potassium, I have 2 on the left, so I'm gonna put a 2 there. Carbonate, CO3, I have a single CO3 here, I have a single CO3 on the right, good to go. Magnesium, 1, 1, good. Iodine, 2, 2, that one is balanced, and that's good to go. All right, last set of ones to look at from our notes. Combustion reactions, there's really a method in balancing combustion reactions, and that is you want to start at the left and work your way to the right. So you want to start with carbons, then deal with hydrogens, leave oxygen till the last thing you balance. All right, so let's take a look. Carbons, I have 1 carbon on the left, 1 on the right, great. Hydrogens, I have 4 on the left, I have 2 on the right. So I need to put a 2 in front of that hydrogen, great. Oxygens, I have 2 on the left. Now be careful, oxygens, you're getting them from 2 places. You're getting them from the carbon dioxide and from the water. So you have to count those. All right, so I have 2 on the left, and then I have 2 from carbon dioxide and 2 from water. So I have a total of 4. Well, I'm gonna put a 2 there. I now have 4 oxygens. I have 1, 2, 3, 4. I'm good to go now with that equation. Let's take a look at our second combustion equation. I have 2 carbons on the left. I have 1 on the right, so I'm going to go ahead and put a 2 there. Hydrogens, I have 6 on the left. I have 2 on the right, so I'm going to go on ahead and put a 3 there. All right, now our oxygens. 2 times 2 is 4, so I'm dealing with 4 from the carbon dioxide, and 3, I'm just writing that really lightly just to remind myself. So that's gonna give me 7. That can be a bit of an issue. Well, because obviously 7's not divisible evenly by 2, but so I say to myself, all right, what times 2 would give me 7, okay? And we know that that is 3.5, right? 3.5 is gonna give, 3.5 times 2 gives us 7. Great, so technically, mathematically, this is now balanced, but I can't leave a fraction as a coefficient. So I'm going to multiply this entire thing times 2. When I say that, multiply the entire thing times 2, I mean that you have to multiply all of the coefficients. Never change what the compound is. So 2C2H6 plus 7O2 yields, that's what you say for the arrow, 4 CO2 plus 6 H2O, and that right there is your balanced equation. All right, and then it all works out. Okay, if you want to take a moment now and pause the video before you move on to the practice problems, and you can go on ahead and give those a try on your own. All right, so I'm going to go on ahead and go through these practice problems with you from your notes. All right, so here we go. So the synthesis of silicon monoxide from its elements. So you are synthesizing silicon monoxide. So this is a covalent compound. You have 1 silicon, you have 1 oxygen. All right, great. So that's your compound. You're making it from its elements. So that's silicone. Nothing particularly different about that one. But oxygen, you do have to remember that that is diatomic. So we write it as O2. All right, great. So now I've written my compounds. I've made sure that they're all proper. Now I'm going to balance. Well, silicones are fine. Oxygen is not. So a 2 and a 2, and I'm balanced. All right, decomposition of sodium oxide into its elements. So I'm taking sodium oxide. All right, sodium is +1. Oxygen is -2. So that's going to be Na2O, sodium oxide. And it's going to break down into its elements. Sodium plus oxygen, remembering it is diatomic. Okay, I've written my compounds properly. It's now time to balance this equation. All right, I can tell my oxygen is going to end up being an issue. Sodium is just a single all by itself. That's going to be really easy to balance in the end. So I'm going to actually pick oxygen to deal with first. I have 2 on the right I only have 1 on the left, so I'm going to go 2, and then I'm going to put a 4 in front of those sodiums. Okay, fantastic. Reaction of silver nitrate, silver +1, nitrate -1. So I have AgNO3, and I'm reacting that with zinc. All right, so I have an ionic compound and I have a lone element. This is a single replacement reaction. All right, ionic compound, lone element. So remember, with a single replacement, you're gonna look at the single and say, what is it? Zinc is a metal, so it's gonna replace the metal in the compound. So that's gonna give me zinc nitrate. Well, zinc in a compound is +2, nitrate's -1. So I need 2 nitrates. Okay, great, zinc nitrate's written properly. Don't forget poor silver here. It's gotten kicked out and it's all on its own. I now need to balance this, okay? So the silvers look good. Then remember I said for polyatomic ions, treat them as an entire entity, all right? So nitrates, I have 1 on the left, I have 2 on the right. So I'm gonna go ahead and put a 2 here. Now my nitrates balance, but now I have to deal with my silver, and I put a 2 in front of there. Zinc's already good to go. All right, and there you have the balanced equation for that reaction. All right, great. So let's go on ahead. Number 4, the reaction of sodium phosphate. Again, sodium's +1, phosphate's -3. All right, so that's gonna be Na3PO4. Lead 4 nitrate, that Roman numeral 4 is telling me that lead is +4, nitrate is -1. So that's gonna be PbNO3, 4. I need 4 of those nitrates. All right, so right here I see that I have 2 ionic compounds. They are going to switch partners. All right, so it doesn't matter which one you want to start with. I'll start with sodium. So sodium's your positive from this compound, or your metal. It's gonna go with the negative from this compound. So it's gonna give me sodium nitrate, +1, -1, so that's fine. Now I have to deal with my lead and my phosphate. Lead is +4, we know that from up here. That's not gonna change from the left to the right. Phosphate's -3. Least common multiple is 12. All right, so I'm going to need 3 leads. I'm just gonna scooch this over a little bit. Okay, and 4 phosphates to give me the proper compound. All right, so when it comes to this type of double replacement reaction, I'm going to give you a little piece of advice. You want to kind of start dealing with the most complicated one and leave the least complicated one. And by complicated, I mean kind of the one with all of the subscripts. The least complicated one till the end. All right, so I want to start by looking here at my lead for phosphate. So I have 3 leads, okay, right here, 3 leads. So I'm gonna go ahead and put a 3 there. I have 4 phosphates on the right, but I only have 1 phosphate. Remember, phosphate is PO4. I only have 1 phosphate on the left, so I'm gonna go ahead and put a 4 there. All right, great. Well, now my leads are good, my phosphates are good. I need to deal with my sodiums and my nitrates. I have on the left now 4 times 3. I have 12 sodiums, so I need to put a 12 right there. And if you notice over here, I have 3 times 4, 12 nitrates, so it works out great. If you find that you just can't balance an equation, chances are that you wrote the formula wrong. So the best advice I have is to just completely erase it and start again, all right, if you find that it just won't balance. Okay, so let's look at some combustion reactions to finish out our notes today. Remember, combustion, I'm going to give you the hydrocarbon. So in this case, it is pentane, which is C5H12. If I tell you it's combustion, it means it's going to react with oxygen, it's going to produce carbon dioxide and water. Always, always, there's nothing to figure out. That's just what it does. When you balance, you're going to start with carbon, 5 on the left, 5 on the right. 12, I have 2 here, so I'm gonna put a 6, great. All right, now your oxygen's last. 5 times 2 is giving you 10 from the carbon dioxide, and 6 from your water, so you have 16. What times 2 gives you 16? That's 8. You are balanced and good to go. All right, last one for us today, combustion of octane. So C8H18. Again, combustion's always reacting with oxygen, always giving us carbon dioxide and water. I'm going to go on ahead 8, so I'm going to put an 8 there. 18, so I'm going to put a 9 there. Great. Now I'm going to deal with my oxygens. 8 times 2, I'm getting 16 from there and 9. So that gives me 25 oxygens. Okay. All right. Well, what times 2 is 25? Remember, this is our trick that we're going to do to figure this out. What times 2 is 25? That's 12.5. Okay. I'm now going to multiply this whole thing by 2, and let me erase my scratch work so I can make this look nice. Okay, so this is going to give me 2 C8H18 plus 25 O2 is going to give me 16 CO2 plus 18 waters, and that would then be my final answer. And it's always good just to kind of double check. All right, 25 times 2 is 50, great. 16 times 2 is 32. 32 plus 18 is 50. That's a really good sign that things went well. All right, so great. You're gonna go on ahead and do a bunch of practice with this in class. Have a great day, everybody.